Yeah, that's great.
Yeah, thank you, Cheryl.
Thank you.
Thanks. So, so that's what we left last time, right? But yeah, I apologize if you feel I'm changing the direction again because I decided to talk about the spectroscopy at this time. So we still have covered some of electronic structure, which is very important, but it's not a very rigorous continuation from what we left last time, right? So I apologize if you think it's kind of scattered, but I do this mainly because I feel I still need to pay attention to the relevance to all the research you do. So I also want to strike a balance between the depth and the relevance, because sometimes what is very relevant to you may not be very in depth, but also I hope that we can go too deep, right? And that we can have some benefit in the future. So that's the motivation why I want to talk about the synchronous spectroscopy, and we have to do this anyway sometime. So another thing is we spend a lot of time talking about the X-ray scattering, right, including both the diffraction and the PDF, and that could be regarded as a major part of what we do in terms of characterization. Another major part of what we do is the spectroscopy. And in the context of synchrotron, we're mostly using the X-ray absorption, but surely that we also use the photon electron spectroscopy, which is XPS. But I think that is probably more routinely covered in many other areas. So I'll just focus on the absorption spectroscopy at this time. And if necessary, we'll expand to the region. At the very beginning, I want to give some of the examples what we did in the past, right? So these are all the works from our group. I picked some of examples which I think could be regarded. There are some typical examples showing how we extract information from those techniques, right? So we can first talk about the transition metal KH, which is in hard X-ray region. Then we'll move on to the soft X region, including both the transition metal LH and the oxygen KH. And I'll just go quickly to show you what kind of information we already got from those kind of experiments and how that really helped us to do the research, right? So the first one is transition metal KH, which is probably the most routine measurement for the spectroscopy, right? We can do that in transmission mode, which is very convenient, and we have a lot of beam time. So for the transition metal KH, I think probably you're already familiar with the fundamentals, but I just want to go through this case by case. So the first one I'm presenting is in fact what I did during my PhD. So I was working on the spinel, and my topic was actually to improve the thermostability of the spinel, which is not stable. And then I realized that in fact we use ion doping, and to now they can improve their thermostability remarkably. And by using X-ray absorption, we can clearly see that once we heat up the sample, so there's a very significant increase of the pre-etch. So we can see here, there's a significant increase, right? So this is indicating of the site, the local environment change of ion from the previous octahedral to the tetrahedral. So as we show here, so in the room at room temperature, the ions are mostly sitting in the octahedral side, but once we heat it up, actually goes to the tetrahedral side. Until now, this stabilized the whole structure in another spinel phase, and suppresses oxygen release, which is a very dangerous thing for their in terms of their thermostability, right? So this is what we got from their hard X-ray absorption. So the second case is a more recent case, relates to the sodium copper manganese oxide that Arthur is working on. And this is the fitting that was done by Shar. So Shar fitted their Fourier transform, their XAS region data. So we can clearly see some of their bond length changes, right, during the charging discharge. What is particularly interesting is we are expecting the bonds to be continuously shortened during the charge state, but that is turned out not to be the truth. In fact, at the end of charge, there's some, in fact, some increase in this short copper oxygen bond. So this, we believe, relates to the participation of the oxygen redox. And that is why we observe this kind of abnormal change during the charging process. The third case is, I think this is also very routine, that we can clearly see the valence change from the edge shift. And we can, this is also relates to Arthur's work on the sodium copper manganese system. So we can clearly see the edge shift of the copper. So usually people regard 0.5 as their edge position, and we can see it changes continually during the charging process. The first one, I do not have a picture here, but personally, I really like this work. And this work was mainly done by the previous postdoc in our group, Xiaolong Wang. He's doing the depth calculation. And what he did in this work is to reveal the correlation among valence change, the edge shift, and electron localization. A very practical thing is, if we do a lot of our X-ray absorption experiment, we realize that sometimes for some elements, they do show edge shift, when we're expecting them to be oxidized, the shift to the right. But this is not always the case. In some cases, when their nominal valences are changing, we do not really see some obvious edge shift like we see here, right? And also like in the case of nickel. In fact, we do observe some kind of a shape change of the whole spectrum that do not show this kind of a rigid edge shift. So what Xiaolong did in his work is actually he revealed this kind of correlation among this kind of seemingly independent phenomenon of valence change, edge shift, and the electron localization. To simply put, if the electron tend to be more localized in the system, then we're more likely to observe their edge shift change from the oxidation process. The other way is if the electrons are delocalized or they're itinerant, then we're not likely to see some rigid edge shift, even though that the transition metals they're oxidized. The next one is the transition metal on LH. So this is within the soft X-ray region, right? And I think probably you know that we can do this at the IOS beamline 23ID. So that is the soft X-ray absorption. What I'm showing here is transition metal LH, and this is also related to iron. It's actually from the same paper that I did during my PhD there. So what we did in this one is actually we can simulate the spectrum by assuming their crystal field, their splitting energy. So you probably can recognize this is 10 dQ is actually corresponds to the crystal field splitting energy, right? So if we have a larger this kind of energy, that means the cations they tend to pair and form the low spin configuration rather forming the high spin, right? So if the splitting is small, then they would not pair, and in fact, instead going to the higher energy orbitals and forming their high spin configuration. And we can simulate that by changing this 10 dQ parameter and obtain the different spectra, at a different crystal field splitting energy. And we can see that typically the experimental data matches well when we choose some kind of a small 10 dQ. This is a kind of small, right? So to put us in the context of their energy scale, if the 10 dQ is about the 3 eV something, that's a very high crystal field splitting energy, then something like, for example, the carbon monoxide or the cyanide, the ligands, they can create such kind of a big crystal field splitting. But for those kind of weak ligands like the oxygen or the chlorine, they usually actually have some kind of a small 10 dQ. So we can confirm this is indeed a high spin iron 3+, and that electronic structure also relates to their site preference of their ion in the whole spin air structure. So I think the take-home message is transition metal IH not only provides about information of the valence, but also like the spin state, which is something we may not be able to get otherwise. The third case is also the soft X-ray region, and that is the oxygen KH. And this is also from Shuilang's work, like Qing just mentioned. In fact, he did a combination of both experimental and theory, and also the matching between them. So what he did here is actually through the experimental measurement of oxygen KH and the DFT calculation, we were able to analyze the itineracy of transition metal 3 elements. So we were able to tell whether the electrons itinerant or the localized in this system, and that relates to how their spectrum changes, both in terms of hard X-ray absorption and also soft X-ray absorption. So I think that itineracy probably could be the keyword that you want to remember from this slide. Okay, so this is some of my thoughts I want to put in here, but I think they probably can be generalized to any characterization method we'll use, right? And this is something I have in my mind, and also I encourage you to think about them when you get your hands on any characterization tool. So first question is, what are we really measuring, right? So for example, for the diffraction, we measure the diffraction intensity, right? And for absorption, we measure the absorption coefficient. So we need to be clear what exactly we're measuring. And that relates to the experiment. And also that relates to how to do this experiment well, how to collect the good data. Because we all know high quality data is the first step, of getting you to have reliable analysis and getting you closer to the true scientific story or exciting science underneath. It has to be started with a good data. Then how to do that? So I think we need to be clear about this and make all our efforts to collect good data. That includes the sample preparation, right? And it is inoperable. It also includes their cell design, right? And sometimes the coordination with the beamline scientists, so that we want to also optimize the condition from the beamline side. The second part is, I think that is very important, is what we really learn from this. So the previous 3 examples, including both including transition metal KH, transition metal LH, oxygen KH, the final answer we want to give, final information is we want to tell the other people, to tell the audience, is that what do we learn from them, right? Did we learn about the valence, about electronic structure, about their crystal structure, or their local structure, or if we're talking about imaging, it's about the morphology, about the chemical distribution, what kind of information we want to deliver. But I hope we do not stop here, because we still want to take a step back and think about what's really the theory behind this, right? What's really the theory that connects what we measure to what we learn, or what kind of information we obtain? So we need to understand the theory. When we were talking about the diffraction and the PDF, we know, we covered the theory of the X-ray diffraction, right? Especially, I encourage everybody to think in terms of the electron scattering instead of probably the old picture, like the X-ray reflecting on the plane, right? Which doesn't really tell you much information. But when you look at the whole picture from the perspective of electron scattering, then you appreciate a lot of the process, like how we have intensity, right? And how we relate the intensity to the atomic position of the structure. That's the power of this technique, and that's also relates to the theory. That I don't think we can get away with that. And once we have the theory in hand, and we really understand that, we have more confidence to analyze the data, right? So instead of just clicking buttons, then we have an idea what we're doing, and we can also even sometimes reflect and optimize the procedure that we do to analyze the data with more accuracy and with more reliability. And so this is some kind of a personal thoughts on the characterization, and I hope probably can also inspire you, to think about them also. So in the specific case of X-ray absorption, what we do in the experiment is we measure the absorption coefficient. So let's take the example of our typical transmission mode, right? So this typical transmission mode, you have the incoming the X-ray, you measure the I0, right? But shortly from the ion chamber, and then after the absorption, then you measure the IT, right? Which is the current of the ion chamber after the absorption event. And then you can calculate this this mu, which is absorption coefficient, and this all are related by this Beer lambda law. So this is kind of a standard absorption their process. So this is the experimental part, right? We do the experiment. For example, in the transmission mode, we want to measure I0 and IT, and we get mu. So this is what we get. So we always do our best to get to the best mu we have. I mean, the best data quality, right? So that's why we want to, change the gas. We make everything ready for the I0 and IT measurement, such that we can get a very decent data quality of mu. So we always push for that. But the other side is the theory. So because we cannot just tell people, we collect a very beautiful data of X-ray absorption. You see, this is data I collect, and people still want to know, well, what we want to tell them about the property of this material, and that relates to the theory behind X-ray absorption. Right? And the standard, the theory behind absorption is a Fermi-Golden rule, so which relates to the initial state, this initial state, and the final state together. And also from this delta function, this is basically actually the telling us it only happens at excitation energy, right? And this is the transition matrix, and this is basically the physics nature of this transition. For example, is it dipole or the quadrupole, right? So it is dipole, then basically we have a dipole selection rule, meaning that actually we have the delta L, the angular momentum should only change by 1, right? So we can only have like S to P or P to D or D to F, this kind of a change. We cannot have it from S to D, right? That's against the dipole selection rule. So this is the theory behind X-ray absorption. We can see that now we have something that we're interested in, or the audience, or the other people interested in, which is the physical property of the whole material, and that is electronic structure. It is embedded in this kind of relationship. And what we really get is something like this. Well, we do not get exact the transition probability, but with a very good approximation, the absorption coefficient is proportional to this transition probability, right? So once we have this kind of a picture, we know that we relate to this something we measure, which is absorption coefficient, to something we are concerned about, something we care, which is our electronic structure. So they're connected in this way. So this is the general picture about X-ray absorption that connects the experiment to the theory. And I hope this kind of pictures is firmly embedded in your mind, that you always think about them in this way. And also I encourage you to think about this when you, for example, when you're analyzing the diffraction data or the PDF data, right? And what's the experiment you're doing. What kind of what are you measuring? What's your measurement? And then what's the theory behind that, so that what you measure can be translated into some abstract property that people are interested in, right? So they're in the context of X-ray diffraction, that is an atomic structure that people want to know. But we do that. We solve that puzzle by measuring the diffraction intensity. So this is how the whole characterization works, and I hope you can always practice having this kind of association between experiment and theory. Well, that is in the perfect world, right? We're living in a very realistic world, so we have a lot of things that make things complicated, and but that's also when the place where our expertise will contribute to solve this problem. There are a lot of practical complications arise. So for example, from the experimental side, what we really measure, as we already showed in the previous example, right? What we really measure is I0 and IT. That is ion chamber current. We're not directly measuring the absorption coefficient. And if it is we're measuring in the fluorescence mode, we're measuring the photons, right? We simply do counting how many photons are coming out. So we measure how many photons we have. They have to be translated, maybe sometimes in a very simple way, but still it's a kind of indirect. It some has to be translated to some the property like the absorption coefficient. But this kind of translation is not always faithful. So, for example, in the when we do the fluorescence yield mode, the outcoming fluorescence, the number of photons coming out is not always proportional to the real absorption coefficient, right? So, if that happens, that means this kind of the correlation, this kind of a chain of a correlation, they are not valid. And we will be having problems to really analyze data, right? And to tell people what's really going on about the electronic structure. That's problematic because our assumption is not valid. So we need to be aware of those situations when the practical complications arise and come up with either the sample preparation or choosing a different detection mode or using afterwards corrections to address those issues. So I'm giving some of the typical issues that we can come across during a spectroscopy experiment, like the conductivity issue, right? So this is typical when we measure, the outcoming their electrons. So if the material is not conductive, then we'd have problem. I think Shar and I just experienced their unhappy part of this issue. So we can see the signal can really varies from sample to sample, even though we assume they have similar properties. And then the beamline scientists suggest us to actually use the carbon tape to cover all of them. So actually we have both the connection underneath and also the connection on the top level. And that really solved the issue. So there are issues and there are ways to address them. And also we have the self-absorption issue, which is typical for the fluorescence yield. And that's also a part of the reason why we sometimes need to dilute sample if we want to measure the fluorescence, right? And also we have some, this is some kind of terminology I invented because I just want to be brief. I call this irrelevant fluorescence because for example, when you're measuring the manganese LH, what you're interested in is manganese. But very typically, there you have the oxygens nearby. And when you shine the X-ray beam on manganese, is actually also doing something to the oxygen. And that comes into the signal of your manganese spectrum. So those kind of processes they're there, and they would violate the assumption that we have at the very beginning. So we have to come up with to address them. Also for the theory part, I think a very easy way for the any calculation is peak labeling, right? So I think many people do this. It's a very convenient way. We just label the peak and find some standard to match to indicate what is this. This is convenient, but it definitely has its own pitfalls. And especially in terms of the X-ray spectroscopy, sometimes you do not really have a clear labeling of this peak, because this peak does not correlate to any of the orbital, because it's not orbital, it's the states. I'll cover this later. So we need to be aware of that. Sometimes there are complications in the theory. Sometimes it's quite simple, right? Sometimes we can do the peak labeling. We can see this peak corresponds, for example, corresponds to 2G, and that peak corresponds to the EG, which is fine in a lot of cases, but not always. Sometimes you cannot find this kind of correlation because it actually is a many electron phenomenon. And you have to consider the many electron wave function, which is totally different from the one electron wave function. So there are issues there. Okay, this is also some of my personal thoughts, and I hope could be helpful to you, because what I realized in my experience that you can never really separate experiment from theory. Or in other words, you can never do a real good experiment without knowing the theory behind it. And the other side is also true. you can never really, apply a theory very elegantly or very powerfully if you do not have a very good experiment to support to give you the data that you want. So actually, they are very closely related, and we can only do a good job if we know what we are doing. So that what I mean is that we need to be aware of each step we're taking, right, and what we are doing. For example, what we measure and what is really happening. So I'm giving here an example of the practical complications I just mentioned about self-absorption issues. So I want to dive a little bit into that and have a more detailed account of what is really going on. I think we have to start with talking about the different interaction between photon and electron with matter. Photon and the electron, they interact with matter in very, very different ways. And that gives rise to a lot of different the practical issues following that. For the photons, is still mostly following the Beer number law that they're actually once we have the photons passing through the material, it will be absorbed, and the absorption is closely related to the thickness of the sample, right? So that's why we can, in fact, calculate how much is absorbed if we have the information of the chemical composition of the material and the mass density of the material. So we can, in fact, really calculate those. But so that's for photon. In general, it's kind of a weak interaction, right? So actually, photon can travel a relatively long distance in the matter. But when it comes to the electron, it's totally different. Electron interacts with matter very strongly, and this kind of the interaction can be well described by the so-called universal curve. So I think this universal curve is something that is well known to everyone who does the XPS, right? When you deal with the photon electron. So what universal curve simply is describing their inelastic mean free pathway, or in other words, roughly how long the electron can travel in material, and how that relates to the energy of electron have. So we can directly tell from the y-axis that you see these are very
sorry to interrupt. I just had one quick question.
Yeah, go ahead.
So the universal curve, the electron mean free path, is it calculated in vacuum?
Yes.
Okay, so if the electron originates, say within the material during the XPS measurement, so how can one calculate how long the electron will flow within the material before it gets into the vacuum?
I think I should take a step back. It's not calculated. In fact, you can see from here, right? It's fitting this scattered dots with a curve. So it comes from a lot of measurement. So this is actually the fitted curve. But once we have this kind of fitted curve, then we can, based on this curve, then to calculate for other unknown systems.
Okay.
Yeah, but can you see your question again?
So I was wondering, when someone calculates the mean free path of electron, so basically the mean free path of electron would be would be measured inside the vacuum, or how long it can, or how long distance it can pass within the vacuum. Can that measurement also take into consideration the passage of electron within the material, say solid material where it originates?
I think I probably answered your question wrong. They are not. I think probably you are thinking about it's how the electron travels in the vacuum. Is that your understanding?
Yeah, I mean, I was kind of wondering. So say if we want to apply this curve to XPS, so if the electron being detected is originating somewhere within the material, it means kind of, I don't know, I'm not sure if it means that the material first have to pass through the material before it gets to the vacuum and then to the detector.
Sure, yeah.
So in that case, I mean, it might be easy to calculate or measure the mean free path within the vacuum. So when this kind of electron has to pass through both the
But
solid.
if it's in a vacuum, there's no matter to intact, right? Then
Yeah. I mean, the origination of the electron, I mean, where the electron is originating, if it is within the material and the electron has to pass through the material, then get to the detector. I'm trying to understand, can that kind of factor also be taken into consideration when calculating the real mean free path? I'm not sure if I have been able to explain my question properly.
maybe I didn't really understand your question clearly. Yeah, if anybody think they understand your question, probably can help me. But maybe I can explain a little bit about the process, right? So, so once you generate electrons, they have to get out the whole system, right? So, but at the very beginning, the electron keeps increasing its energy, then is getting rid of the bound of the whole system. Then when it actually has energy greater than the work function, then it can escape from the solid and into the vacuum.
Okay.
Yeah, that's the whole process.
I see. Okay.
Yeah,
Sounds good.
I don't know if that helps you to answer your question.
Yeah, it does to some degree. Yeah.
Yeah, maybe when I can send you a picture offline there, showing you the whole process, how the electron that was originally sitting in the solid, right? Then finally became the electron that escaped the solid. That's a process, right?
Yeah. Sounds good. Thank you.
Okay. So I think the key information I want to deliver here is that we need to remember electron interacts with matter very strongly. And that relates to the very short elastic mean free pathway, roughly how long the electron can travel in the matter, right? And that's also at least one of the key reasons in those electron-related detection mode, we normally only probe the very surface. So whether you are measuring the, for example, the total electron yield from X-ray absorption, or is a photon electron from the XPS, we're basically probing the surface, right? But surely, depending on how much the kinetic energy the outcome electron has, then we have this a little bit differentiation of the depths, but they roughly, they all fall in their surface region, covering only nanometers, several nanometers. Okay. So, in fact, I think this slide is important, and this is directly relates to doing experiment for the soft X-ray, and they're understanding why your data sometimes look terrible if you choose the wrong method, or you chose the wrong detection mode, right? So we know that in soft X-ray we have the both total fluorescence yield and total electron yield. For those who do the X-ray absorption a lot, you definitely would have experienced that your TEY usually looks much prettier than your TFY, right? The TFY probably is very noisy, and the TEY, wow, very nice data. One intrinsic reason behind that is the electron yield has much more yield probability than the fluorescence yield. So if we're talking about their energy region of like hundreds of EV or several hundreds of EV, the probability of electron yield is about 99%, and the fluorescence yield is about 1%, which means you have a much more electron yield event compared with the fluorescence yield event, and that's why your fluorescence yield typically looks noisy, right? But sometimes we have to do the fluorescence yield because, as we mentioned in the previous slides, and fluorescence yield really is about the photons, and they have they can travel much longer than electrons, so they can tell us information about the more depths. So we still want that, but there's some intrinsic sometimes some pitfalls about their fluorescence yield. So let's look at this picture, okay? So this is the total fluorescence yield, and we need to be aware that the probed depths is roughly proportional to the absorption lengths, right? So you have the photon coming in, it will attenuate as they travel through the solids, and at some point, kind of diminishes, or to like only 1000% of the original flux. So we can regard this as kind of diminishes and it vanishes. When we have the X-ray at the energy before the edge, right? So we have the photon in, photon out, the detection mode. We're collecting the photons. We need to be aware of that. So this here, this probed volume is basically determined by the Beer lambda law, right? By determining how long the photon can travel. So this is what happens before the edge. But when it comes to the at the edge, the energy. So now we're moving the energy up. So now we come to the point where the absorption, where the exciting energy is following the region of the edge energy of this element. For example, if it's for oxygen, is 530 eV something, right? So once we have this region, there's a lot of absorption along the way, because now the absorption event, the absorption yield is much higher than when we have this kind of a non-resonant absorption, right? This is non-resonant, meaning that your incoming X-ray energy does not have the same energy as the absorption edge, but now they are of the same energy. Then you have this resonant absorption, and your absorption length is much shorter than the previous case, right? Everybody is fine with that? Okay, so then now we can see the problem. The problem is, in the previous case, you are probing this volume, right? You're probing this area, which is big. But now, in fact, the X-ray is only probing a small region. And if we compare this to, you're basically probing the different volume of area at these two energy positions, right? And this is validating your assumption, because our assumption that we're always probing the same volume of the material, right? Such that your absorption coefficient only relates to how much is absorbed because of this resonant absorption. But now your whole volume changes, right? So they're no longer can be related directly to the absorption coefficient, and that causes the problem. But also, as I mentioned, people have already found the solution to this, which is the IPFY, the inverse partial fluorescence yield. So by changing the detection in a different mode, we can get around with this. And this capability is available at iOS. So yeah, this capability is something actually the beamline scientist Adrian is proud about. In contrast, if we look at the TEY, which is the electron yield mode, right? So what we have is we have the photon in, but we're detecting the electrons. So it's actually a photon in and the electron out mode, and we're detecting the electrons. We still have this problem, of changing the probed volume, moving from before edge to after edge, right? We probe a very large region here, but now we're probing a small region. But it doesn't really matter, because no matter how much you probe, you can probe, but the electrons that are capable of coming out only comes from this small region, right? So they're kind of independent of the touched region of the X-ray. They only relates to what electrons can escape, and only this part of electrons they can escape out, no matter whether you change the probe volume a lot. So that's why the TEY is actually much less sensitive to the self-absorption issue, and you typically do not meet the self-absorption issue for the TEY compared with the TFY. Okay, so this is one example that of the practical complication during the X-ray absorption measurement, especially for the soft X-ray. The next hour, I think I still have 2 slides. Yeah, and the next one, I want to talk a little bit about complication from the theory side. So when it comes to the theory of the behind the spectroscopy, is always Fermi's golden rule. So I think in some sense it's kind of easy, right? It's a simple equation that really tells you everything about what is really going on, but it's kind of disguisingly simple. But first we can look at what's really this equation is telling us. So this is a transition rate. As I mentioned before, this is proportional, generally proportional to the absorption event, or to the absorption coefficient that you can get. And this is the final state, right? So I'll explain what do we mean by final state, why we do not talk about the final orbital, right? But we talk about, okay, you have the 1s to 2p, that's talking about orbital, but why we use the word state here? I'll touch on that a little bit. And here is actually the transition matrix. It's a physics term. You can find, spend time trying to understand what really is if you want. But at the moment, you can just accept that this is a transition matrix describing the physics nature of this transition, right? Whether this is dipole transition, what we show here is dipole transition, but there are also like quadrupole transition and other transition process. And here we have the initial state. So that's the state where when the system is prepared at the very beginning, or we can call it the ground state, right? So we have the ground state, and then we have the photon come in and exciting the whole system, and then through some relaxation, and it changes to another state, which is the final state. So here, final state and initial state are there correlated or connected by their transition matrix or the transition operator. And this is a delta function. It is basically saying that this whole absorption event will not happen unless at the when your incoming energy satisfies this kind of relationship that you can excite the core electron to appropriate energy level, and that's I think that should be easy to understand, right? So for transition metal KH and oxygen KH, the absorption event of this transition rate of their absorption coefficient we measure is generally proportional to the unoccupied density of states. So we can imagine that you're pumping your core electrons to the to the unoccupied states, right? So if we want to explain the intensity, so the first thing is definitely you need to have unoccupied states. They need to be available. If you do not have available unoccupied states, then there will be no intensity. So one example is actually the zinc. So zinc 2+ is a 3d10. There's no d states that is unoccupied, right? So if you measure the KH for zincs, you will not observe any pre-H. It's a very flat one because there's no states to go. So that peak intensity is 0. So the availability of unoccupied states is one thing that determines intensity. The other thing is the symmetry, because as I mentioned, this is a dipole transition process, and then you have to satisfy the dipole selection rule, which means that your angular momentum has to change by 1. So if you're exciting the 1s electron, it has to go to p orbitals. It is 2p or 4p, right? Depending on the energy. And if you're exciting from the 2p, the p orbital, it has to go to the d orbitals. So it has to go to the orbital that has the appropriate symmetry. But normally we talk about is actually the states, which actually has a combination of the from different orbitals. So that depends on how much, for example, if from S to P, how much p symmetry element you have in this unoccupied state, right? So that's basically the origin of the peak intensity. If we have this kind of the 1 electron picture, which is valid for the transition metal and oxygen KH, but it is for the transition metal LH, the picture is totally different. And now the absorption coefficient of the peaks, they're no longer corresponding to the unoccupied the density of states. The reason is that, as we can see here, we're talking about the initial state and the final state. And if we talk about this final state, then we have to describe it with a 2p hole, because now there's a 2p electron excited out, right? So there's 2p hole left, and there is a 3d valence electron added. And if you write it in terms of wave function, there is a strong correlation between the 2p hole and the 3d the valence electron, and that kind of correlation would violate this kind of a one electron picture. Then you can no longer correspond the peak intensity to the density of the unoccupied state. So, but in this case, we still have a theory to describe this, and that's called the multiplicity theory. So the take-home message, before I get you too confused about what is really going on, is I hope you understand that, first of all, understanding orbital is not enough, right? But we need to know the origin of 1s, 2p, and 3d that people normally talk about. Yeah, that's something we need to start with, but that's not enough to understand the spectroscopy. To understand the spectroscopy, especially for understanding the transition metal LH, we need to understand what is really about talking about the states. And the states is basically what I mentioned in the previous lecture. It all boils down to the solution to the Schrodinger equation. Simply that in those systems, the Schrodinger equation is more complicated because we're dealing with many electron systems, and they're not just simply the multiplication of the single electron wave functions, but they're more complicated than that. But people have dealt with it, and they're in the field of spectroscopy, and that usually described by the term symbol. So I think some time ago I gave a lecture about the term symbol, but we probably can go over it or review it at some time at some point in the future. Okay. Oh, that's the end. Yeah. So I think yeah, I'll end today's lecture, and please feel free to ask questions.
Oh, I have a stupid question. So I'm wondering, what's the difference between like PFY and TFY? Like all those like total yield and the partial yield. I mean, what's a part of that? Yeah.
That question is not stupid, right? It's a very good question there. So whenever it comes to the term partial, it very likely associates with the kinetic energy. For example, like in your question you mentioned about PFY and TFY, right? So T stands for total. So I do not care, what's the kinetic energy each specific photon have. I simply just count all of them, right? So that's why it's total. But when it has the P in front of the Fy, which is partial, it starts to discriminate against the kinetic energy, right? So because your outcoming photons would have a very diverse spectrum of kinetic energy, depending on their specific the decay process they chose. So we can have a detector to differentiate that, and I can only collect or count the photons that fall within their kinetic energy region I define. And because the photons with different kinetic energies, in fact, also relates to their origin, right? So you can have some kind of a more specific association with the photons you count and their origin, or in other words, the depth you probe. So you can be more discriminative, against the exact depths you collect. That also applies to the partial electron yield. And we have the partial electron yield. So instead of, I simply mirror the drain current, right? That's what we do at IOS, and they simply, mirror how much current is coming out. And now actually I also differentiate the kinetic energy of the electrons. And generally speaking, if you have a higher kinetic energy, that means actually they're coming from a more surface area. So that's why your PEY is typically more surface sensitive than your TEY.
Oh, I see.
Yeah.
Thank you.
And also, by the way, for the fluorescence, if you want to differentiate the fluorescence, the photon kinetic, then you have to use a very different detector, which is a vortex detector. and that can be very expensive.
So that's why we normally just get the total fluorescence yield, right?
Yeah, that's very easy, right? You simply do the counting, and and in fact, I think your question also relates to another topic about the RICS. So RICS is simply a more, the detailed discrimination of the kinetic energy, right? So instead of you simply you do also just do the counting, you do not care about kinetic energy. Now you even plot the histogram of this kinetic energy. So for example, if you measure the oxygen KH RICS, right? Now you have the incoming X-ray, let's say at the 531 eV. Now you would generate a lot of photons coming out, right? Let's say you have 1 million photons coming out, and those photons, have this kind of distribution of kinetic energy. And what the RICS is doing is actually they want to plot this histogram. So at each specific excitation energy, let's say 531 eV, then I will actually draw another, the histogram of the outcoming photons. For example, I probably have like say 5,000, have the 100 eV kinetic energy, and I have like let's say 500,000 at the 200 eV energy, right? Then you have this kind of a histogram of how many photons you have versus their specific kinetic energy. So then you have it changes from this kind of a 1D picture or 2D picture into the 3D picture. So that's the essence of RICS.
Thank you. Yeah.
I just had a couple of quick questions.
Yeah.
So I was wondering how, so you had this simulated transition metal LHS, right? So I was wondering how you performed those simulations. For this one. Yeah. Or the calculator.
This can be done using a software called I'm sorry, I forgot the name because it was done a long time ago. I think it's, but anyway, you can search the name Eli Stavitsky. Eli Stavitsky is the beamline scientist of ISS.
Sorry.
Yeah, Eli Stavitsky. Or you can, you can directly search who is the lead beamline scientist of ISS beamline. His name is Eli, and his last name is Stavitsky. Eli Stavitsky, he is the first author of that software.
I see.
So I think you can easily find that software by searching his name.
Oh, okay, and it is also free, I guess.
It's free and it's based on MATLAB. So you need to install some of the MATLAB modules, to enable that. But I think those modules should be free.
Okay, sounds good. Thank you. And I was also wondering about the self-absorption. Is there any elemental selectivity with it? Like some element will be more self-absorbing than the other?
More absorbing?
Like for self-absorption, I mean, is the self-absorption phenomena, does it depend anyway on the element? Like, for example, iron will have some different self-absorption than manganese, or manganese will have something different than copper, and so on.
I don't really think they're more elemental specific, but I probably can think more about that. Yeah, because generally speaking, it's only caused by you have a more strong absorption at the edge, right? At the edge energy.
I see. So I was asking this question because so the Softex says that I had been doing previously with Fong at SLAC. They always had this problem with the manganese LH at the FY mode. They so claiming to be a self-absorption problem, absorption behavior. But some other elements like nickel or cobalt will have lesser of that problem. So that's why I was asking.
Well, that's good. Yeah, that's good to share. Well, yeah, I think now we can be more clear about this discussion. The manganese typically has problem because its L energy is too close to the oxygen 2K.
Oh, okay.
Right. Yeah. So once it's above 600, is 600 something, right? But it's not far away from the oxygen KH. So once you excite manganese LH at the 600 eV something, you're actually also exciting a lot of our oxygen fluorescence, right? But Well, I think we can be more clear about this. But when you move to nickel LH, which is about 800 EV something, and now oxygen is much more transparent, in the eye over 800 EV, right? So, and there, in other words, 800 EV is doing a minimal an oxygen fluxes excitation compared with what you do at a 600 EV for manganese.
Yeah.
Right.
Makes sense. Okay.
And then, you normally do not have any problem for nickel LH.
Okay, makes sense.
Yeah.
Thank you.
Okay. Any more questions, Arthur and the Dean?
Yeah, if I may, could you I haven't heard of this, the connectivity issue, and you said it happened. Could you I guess elaborate more on, like, yeah, I guess it wasn't fully conductive, but what you saw in the data that like led you to believe it was a connectivity issue?
So conductivity issue, really relates to the electron yield, right? So we're measuring the electrons, and also that relates to Momina's previous question. So if we have some understanding how the electrons escape from the solids, they have to escape from the solids, right? Through the excitation. And if they're not conductive, it's not easy for them to escape. Then what we have to do is actually keep, increasing energy. That's basically a charging process. So in practice, if what I suggest you do is you do not always normalize the spectrum, right? You do not always, do the first thing is to not take a normalization at the first step. In fact, you can actually just do not normalize and put your spectrum together. Sometimes you can see a huge variation in the post edge. So normally when you see something like that, then they may likely to have, they're actually the conductivity issue, that the electronic conductivity can vary largely from sample to sample. The way to address this, I think Shar probably has more first-hand experience to share, since she just done experiment at iOS. At iOS, they give us a copper plate, and they just measure the drain current. But turn out that's not, even that is not helpful sometimes. And what they suggested is actually they suggested to use our coupling tape, to cover alt tops. So actually, those samples, and they're not connected from the bottom. They have their electric circuit, their outlet in the bottom, but also they have the outlet from the top. Right. So yeah, if you're interested, you can reach out to Shar, and probably Shar can even send you a picture, of what we did during this time, the experiment. And that would make a lot of difference.
Okay.
Yeah, and also that relates to the XPS, right? So sometimes we also have problems, similar problems for the XPS. Yeah, whenever we're dealing with the electrons, then sometimes the conductivity issue, can come in.
Okay, thank you.
Yeah.
Okay, any question from Dean?
Yeah, I have also some question. The first one is in this slide, I'm not familiar with the simulation process. I'm not sure what this ligand field physically means and how it's related to the splitting of the peak.
How that relates to what?
The splitting of the peak.
Oh, splitting of peak. Oh, okay. The calculation is easy. Yet simply it's basically inputting numbers, and you click some buttons, then the software just automatically generates a spectrum, right? So that's pretty easy stuff. The challenge part is probably is about the second question, is the understanding of the ligand field, right? And that relates to the electronic structure. There's no easy way to get around that, and I cannot answer that in just a few sentences. But generally speaking, that's describing how the transition metal 3D orbitals actually is split in the presence of the neighboring anions, right? If it is just isolated, you have the spherical symmetry, but once actually they form bonding with anions, forming, for example, the octahedral symmetry, then 3D orbitals that will split, and they have their like T2G or EG. And to go further, then people incorporate molecular orbital theory with the crystal field theory. So actually now then we can talk about the strengths of the ligand. And those things can be very practical. For example, we probably all know that their transition metal can form very strong bonds with their carbon monoxide, right? That's part of the reason why their carbon monoxide is toxic. And also they can form very strong bond with the cyanide, right? And also that relates to, because they have a very strong their ligand field, the strengths, they can pull this kind of splitting very strongly, right? So, but that's something that can only be understood by probably going through some of the textbooks and some of the materials. And that relates to the site preference. So once you have a different spin state, your cations will have a different preference. For example, if the low spin is very likely to happily sit in the octahedral environment. But if it's high spin, then it might have a strong tendency to go to the tetrahedral site. Right? So that relates to the structural material. You asked about the peak splitting. As I talked in the final slide, this is transition metal LH. So the peaks, they are not very obvious. They cannot be directly correlated to their electron orbitals. So there's no easy way to explain why they split. There's simply no easy way to do that. And the whole thing is actually is done through the calculation. Or we cannot say, okay, they split because there's more orbitals. It's not that. It's not as easy as that.
Okay, thank you. Also, in the last slides.
The what?
In the
Last
slide.
slide.
Last slide. This one?
Yeah, I have some question about initial state. So for LH, does initial state always means it's the 2p orbital? Is that how the calculation is done? Yes.
Yes. Yeah. Yeah. You have the 2p3d, right? You have the 2p, which is full. We have the 6 electrons in 2p. And let's say it is iron, then let's say you have 5 electrons, right? You have a 3d5. That's the 2p3d5 is the initial state. Once it generates this absorption event, then you're exciting the 2p electron to the 3d, right? So now you have a 1 electron in 2p and also a hole, right? So you have a 2p hole and you have 3d6. Now, instead of the original 5, now you have an extra electron in the 3D. Then the final state is actually the 2p hole plus the 3d6. And those kind of the kind of a configuration has to go to the calculation of the final states.
So just one more question. Does Fermi's golden rule, it also works on M edge, right? Just curious.
Yes. Yeah. As long as there is an absorption event in nature, the Fermi's golden rule applies to all of them.